The next math concept we're going to look at is called the greatest common divisor of two integers. So to motivate this, we're going to look at reducing fractions to think about how common divisors are used. We're going to then define what it means to be the greatest common divisor of two integers. We're going to compute some greatest common divisors, and then we're going to define relatively prime and show some examples of integers that are and aren't relatively prime. All right, so let's get going thinking about fractions. So if you have the fraction 18 over 30, that is, of course, not a reduced fraction, or not what we would consider reduced or simplified. So the question is, how do you reduce those fractions? Well, basically what we do is we factor the numerator and denominator in some way. So the way I'm going to do it is I'm going to factor 18 into 6 times 3 and 30 into 10 times 3. And then what we can do is cancel those 3's to get 6 over 10. And we don't get a reduced fraction in this case, but we get a more reduced fraction. The idea is we want to factor the numerator and denominator so that we could see that they had a divisor in common. So what we mean in general is if we have two integers a and b, we say that d is a common divisor of a and b if d divides a and d divides b. In other words, if d is a factor of both a and b. And one way you can think about this, if it's helpful, is you can think of a common divisor of a and b as a number that we can cancel whenever we have the fraction a over b. All right, so of course, for 18 over 30, it turned out that 3 wasn't the best common divisor. And best is an opinion, right? But I mean the best for getting a completely reduced fraction. The best one we could have done was 6. Right, so if we took 18 over 30 and instead wrote it 3 times 6 for 18 and 5 times 6 for 30, then we can cancel the 6 and get a completely reduced fraction. Right? So here, what was so special about 6? Well, 6 happened to be the largest of all the common divisors of 18 and 30, and that is going to be important to us too. So if a and b are integers, we say the greatest common divisor of a and b, and we write that as GCD of AB, is the largest of all the common divisors of a and b. So you look at all the common divisors of a and b, put them in a list, take the biggest one, that is your GCD. So from our fraction 18 over 30, we saw that GCD of 18 and 30 was equal to 6. So, and just like before, if you want to think of this in terms of fractions, you can think of GCD of a and b as the largest number that we can cancel in the fraction a over b. All right, so now in general, how do we determine what the greatest common divisor of two integers is? Well, we have kind of an obvious strategy, not very imaginative. We could just try out every number that's smaller than a and b, see which ones divide evenly into both, and then make a list of those, and then see which one's the biggest. This is, it's dependable, but it's pretty long, pretty tedious, and in general, not very efficient at all. Another way we can do this, however, is look at the prime factorization of those numbers and see what kind of prime factors they have in common. So let's do this with an example. So let's suppose we're finding the GCD of 360 and 336. Not obvious what the greatest common divisor of those is going to be, so we might want to try making prime factorizations. So let's first work on 360. Well, you could tell it's even, right? So we can factor out a 2. We get 2 times 180. 180 is still even, so let's keep on going. 180 is 2 times 90, so we get another factor of 2. 90 is even. Let's just keep going with the 2s as long as we can. 2 times 2 times 2 times 45. Okay, we ran out of 2s, but actually 45 is pretty easy to factor. It's 9 times 5, which is 3 times 3 times 5. So we get 3 factors of 2, 2 factors of 3, and 1 factor of 5 in our prime factorization. We go through the same process in 336. Here we have a lot of factors of 2. So we get 2 times 168, 2 times 2 times 84, 2 times 2 times 2 times 42, one more time, 4 factors of 2, and then 21. And then 21 is 7 times 3, which are both prime. So we get 4 factors of 2, 1 factor of 3, and 1 factor of 7. Now, if we want to figure out the GCD, what we're going to do is we're going to look for what prime factors are in common. So they both have 2's in them, right? So if we're looking at 360, that has 3 factors of 2, 2 to the third, right? For 336, that has 4 factors of 2. So between the two of them, the common factors of 2, the biggest we can get is 2 to the third, 3 factors of 2. All right, so if we do the same thing with factors of 3, 360 has 2 factors of 3, 336 just has 1 factor of 3. That means our GCD is just going to have 1 factor of 3. All right, so here's what we have so far. We have 3 factors of 2, 1 factor of 3. Any other prime divisors, and we kind of lost the prime factorization up there, but the only other factors that we had were 5 and 7, and neither of those is common to both of them. So no more prime factors in common, but that's okay. We got plenty. Our GCD is then going to be 2 to the third times 3, which is 24. So if you get a prime factorization, then finding the GCD is actually pretty straightforward. However, we should note that when the numbers get pretty big, factoring can become difficult. Even finding a prime factorization can be tough. So this strategy is only going to take us so far. We are going to, however, find some better strategies in a little bit. All right, so let's go to a related, or a concept that is related to GCD, and that has to do with integers being relatively prime. So let's go back to reducing fractions. And the question you might ask is, okay, so we've reduced fractions. When do we stop? Under what conditions are we finished reducing? When have we gotten to our most reduced form in the fractions? Well, one possible way of saying this, maybe, it seems, when there are no numbers left to cancel. Only this turns out to be impossible. It turns out no matter what your form your fractions in, there will always be at least one number to cancel. And I'm going to be smart alecky about it. So let's see what we have 2/3. So you may think that I can't cancel anything out of 2/3. They don't have any factors in common. Well, they do, right? I can factor 2 into 2 times 1, 3 into 3 times 1. I can cancel the 1s and get 2/3. Now, factoring those into 2 times 1 and 3 times 1 didn't give me a better fraction, so it didn't do anything. But I did have some numbers left to cancel. The thing is, though, with 2 and 3, they're in their most reduced form. The only number I had left to cancel was 1. Right? That was literally the only one I can do. So this is going to happen when the GCD of A and B is 1. So when were we finished? When the GCD of our numerator and denominator is 1, and that takes us to the concept of being relatively prime. So we say that 2 integers A and B are relatively prime, and sometimes we say coprime. I mean, relatively prime, coprime mean exactly the same thing. That happens when the GCD of the 2 numbers is equal to 1. So we can think of this in terms of the GCD, or if you'd rather think of it in terms of fractions, you can think of A and B as being relatively prime when the fraction A over B is a completely reduced fraction. So let's look at some examples. So let's look at 4 and 6. Are those going to be relatively prime? Well, no, they're not going to be relatively prime. They do have a common factor of 2. 2 divides into 4, 2 divides into 6, not relatively prime. For 3 and 5, those actually turn out to be prime numbers, and not surprisingly, those are relatively prime. So if you look at the GCD, the biggest common divisor that you could possibly have is 1. If we look at 12 and 20, those are not relatively prime. We have a common factor of 4. Actually, we don't even have to, 4 is the GCD, but even if you say, well, there's a common factor of 2, that's enough to say that it's not relatively prime. Now, I don't want you to think that the only relatively prime numbers are actually prime numbers. So here are 2 numbers that are actually, they're relatively prime, but they're not prime in themselves, right? 12 is 2 times 2 times 3, and 25 is 5 times 5. However, they don't have any factors in common except for 1. So these are relatively prime, even though neither 12 nor 25 is prime by itself. So remember, relatively prime doesn't mean prime. It just means that they don't have any factors in common except for 1. All right, so now I think you're ready to work on the activities for greatest common divisor. Those are on the PDF file included with this video.